We've talked about reactive programming techniques and how they can be used to build systems that are reactive or perhaps build systems that aren't reactive. One of the tools that I want to talk about specifically, which is a reactive programming tool, is something called the actor model. Now, the actor model is a programming paradigm that supports the construction of reactive systems. Again, like with any other reactive programming tool, just because you use the actor model doesn't necessarily mean you have built a reactive system. You still have to keep those high-level architectural goals in mind. You have to build according to the reactive principles. However, it does provide facilities to very readily support all of the reactive principles. So first off, the actor model by its very nature is message driven. When you build systems using the actor model, all communication between actors is done using asynchronous non-blocking messages. So that's one checkbox that we can check on the reactive principles. It also provides abstractions that give us elasticity and resilience. Because of the fact that it is message driven, it makes it very easy to make it elastic and to make it resilient. And so there are a number of facilities inside of the actor model that allow you to do that. And that includes things such as location transparency is one of the big ones. And we'll talk about that shortly as well. And because of the fact that it is message driven, it is elastic, it is resilient, it can be used to build responsive software. So on the JVM, we have something called ACA, which implements the actor model. And so that is an implementation of the actor model that we can use to build reactive systems. It is the foundation of other reactive tools such as Logem and ACA streams as well. Just to give you a little bit of history of the actor model, if you're interested, the actor model was not created by ACA. It actually has a very long history. It was created in the early 70s by a man named Carl Hewitt. And the basic idea is that the principal abstraction is encapsulating all computation inside of an actor. In the 70s, the idea wasn't necessarily taken to its full extent due to hardware constraints and things like that. However, later languages evolved that were allowed to use it better because of newer hardware. And so now, as we're moving into the more distributed environment of the modern world, the actor model is making a bit of a resurgence as people realize that it is actually very valuable for building distributed systems. So what are some of the fundamental concepts of the actor model? First is that all computation occurs inside of an actor. So at some point in your application, you are going to have one or more actors, ideally more than one. A single actor is not actually that useful. So you will have some combination of actors, and all your computation will occur inside of one of those actors, or across many of those actors. Each of those actors is addressable. It has a unique address. And those actors communicate only through asynchronous messages. That is the only way they can talk to each other. Now, the message-driven nature of actors provides us something that we call location transparency. Our actors communicate with the same technique, regardless of location. This means that local versus remote is mostly about configuration. So if you look at our little diagram here, we have a couple of green actors and we have a green router. That router can actually just be another actor. But what we have is when you want to send a message to an actor, you send it, for example, to that router. That router is then going to route those messages to some number of routees. Now, in this case, we have one routee that is living in the same JVM. You can think of the dotted lines as representing a JVM. So you have a green actor that is being routed to, but you also have two blue actors which are remote. They live in a separate JVM, but they can still act as routees. Now, from the perspective of the original actor sending the message to the router, he has no idea where that message is going to go. He's going to send the message to the router, and the router is going to figure out where it goes. So it may go to a local actor or it may go to a remote actor. We don't know. And because of that, we have what we call location transparency, which is the original actor sends a message with no knowledge of the location of where that message is going to go. it doesn't use a specific technique to send to a remote actor. There isn't a different API to send to a remote actor. The API is identical no matter whether it's sending to a remote actor or a local actor. And that is the essence of location transparency. So again, local versus remote becomes mostly about configuration. It's about saying that this router can route to these routees. The actual communication mechanisms don't change at all. This enables actors to be both resilient and elastic. The way that it does that is because now we can deploy those actors across multiple pieces of hardware, which means they are resilient. If one of those pieces of hardware fails, that's okay because we have other ones to fill in the gap. It also allows it to be elastic because if we have a high level of load, we can simply add more routees on more pieces of hardware, giving us elasticity. Or if we need to scale down for some reason, again, we can remove some of those remote JVMs, and that allows us to scale down. So we are elastic at that point. Now, location transparency shouldn't be confused with transparent remoting. Transparent remoting basically tries to take remote calls and make them look like local calls. So everything looks like a local call, even though it may be remote. What this does is it hides the fact that you're making remote calls, and as a result, it can hide potential failure scenarios. You might have network failures, for example, and because it looks like a local call, you won't know whether there's going to be a network failure or not. You might not think to deal with that possibility. Location transparency, on the other hand, takes the opposite approach. It makes local calls look like remote calls. This basically means you're always assuming that you're making remote calls, which means you have to assume a remote failure scenario could occur, like network failures and other types of failures. Basically, you can't make the assumption that the message is guaranteed to be delivered, and you have to assume that there's a possibility of failure. So, the actor model is important in many ways. There are many reactive programming tools. We talked about a number of them: Futures, Streams, RX Java, RX Scala, those kinds of things. Most of them support only some of the reactive principles. So they may communicate in an asynchronous, non-blocking way, but they don't really have facilities to give you the ability to scale up, scale down, or be resilient. You often have to combine different technologies if you want to build a reactive system. So you might use your reactive programming tools, but then you need to add other things in, like load balancers and things like that, in order to make sure that you maintain the elasticity and the resilience. The actor model provides facilities to support all of the reactive principles. It is message driven by default. The location transparency is there to support elasticity and resilience through distribution. The elasticity and resilience then provide responsiveness under a wide variety of circumstances. Again, it is still possible to write a system with the actor model and not be reactive, but with the reactor model and the tools that are based on it, you're further along the path to success. You have a number of things that you can use just with the actor model alone that will get you to building a reactive system. Now, what if we wanted to build a reactive system without actors? How would we do that? It's still completely possible. We're not going to imply that you need the actor model in order to build a reactive system. So in this diagram, we have our services, and they are stuck behind a load balancer with some sort of service registry. So this gives us location transparency. When we talk to the load balancer, we don't know how many machines our service is deployed across. We don't know how many instances of the service there are. We don't know where they live. We're just talking to the load balancer. So we get some location transparency through that. We also then add in a message bus. This gives us the ability to communicate using asynchronous non-blocking messages. It also gives us some location transparency as well. So we get that through the message bus. The combination of the load balancer and the message bus give us the ability to be resilient and elastic. We can deploy many copies of our service, whether we're scaling up or scaling down. And we can do that across multiple pieces of hardware. So in the event of failure, we can recover from that. So this gives us all of the things that we need. We've got asynchronous non-blocking messages. We are resilient and elastic, and we can use that to build a responsive system. So we have a reactive system. However, the components here are added on rather than being built in. We didn't start with the necessary tools. We had to add all of them in. It requires additional infrastructure. So we've got a service registry, we've got a load balancer, we've got a message bus. All of these things are there in order to provide us what we need to build a reactive system. And the final thing is this results in a reactive system, or a system that will be reactive at the large scale. So it's reactive at the scale of microservices, but it's not necessarily reactive within those microservices. And that's one of the key differences with the actor model. The actor model can be reactive at the level of actors, and actors are within a microservice. You can have many actors within a single microservice. Whereas using these tools, you have built something that is reactive at the level of microservices as opposed to internally. It's still possible to build something that is going to be reactive at the level of components inside that service, but it gets a lot harder. Whereas with the actor model, it's very easy to do that. So, what this boils down to is you can build reactive systems without actors or without the actor model. But if you start with a very strong foundation like the actor model, it's going to make a lot of things easier later on.